Good morning everyone. Welcome to this another video lecture of this course. Today we're going to learn about recurrence relation and how to solve them. So before going to the topic of recurrence relation, let's recall the concept of sequences. So in this course we have studied that a sequence can be defined based on a mapping or a function from a set of a natural number, which is a subset of integers, and it may or may not include the zero, to a given set S. And by using this mapping, then you can define a sequence based on this symbol. You can say my sequence is A of n, where the first term of my sequence is A1, second term is A2, third term is A3, and so on. So any nth term of this sequence can be given based on this mapping that A of n is given by f of n. When you define your A of n equal to f of n, which represent the nth term of this sequence, so you use an explicit way. Okay, you use an explicit way to represent this sequence where the nth term is generated by based on this formula which you have inside this function f of n. So if you take an example where my f is a function defined from a set of natural number to a given set S, and f of n is defined by the expression 1 by n. So I can choose this f of n to define my nth term of the sequence, which is written here, that A of n is going to be equal to 1 divided by n. So I can generate this sequence by passing this input value of n starting from 1 all the way up to infinity. So my A of 1 is going to be equal to 1 divided by 1. So that means the first element is 1. A of 2 is going to be 1 divided by 2. So the second element is 1 divided by 2. So the third element of this sequence is 1 divided by 3. And the fourth element is 1 divided by 4, and so on. So this way I can generate a sequence where my sequence is defined based on a given explicit formula to define their terms, okay, and that explicit formula is given by this term 1 by n. So far we have seen that the sequence can be defined based on the explicit formula. In this lecture we are going to learn another way to specify a sequence where one or more terms or more initial terms are given. Those becomes your initial conditions, together with a rule for determining the subsequent terms from those that precedes them. Okay, and this is basically an idea behind your recurrence relation. So let's take an example where the initial term is given to us, which is A of not equal to 2, which is the first term of my sequence, and a rule is given where the nth term is connected with n minus 1 terms based on this relation that A of n can be written as A of n minus 1 plus 3 for every value of n greater than equal to 1. So if you follow this rule and using this initial term A of 0, so A of 0 is given to us as equal to 2 if you follow this rule for n is equal to 1. So from there you can say A of 1 is going to be equal to A of 0 plus 3. A of 0 is already 2, so A of 1 becomes 2 plus 3, which is equal to 5. Then I can reuse the same rule and I can compute my second A of 2 term. So A of 2 from this rule is going to be equal to A of 1 plus 3. A of 1 is 5, so 5 plus 3 is going to be equal to 8. And similarly, I can compute my A of 3 term, and A of 3 is going to be equal to A of 2 plus 3, and A of 2 is 8, so 8 plus 3 is going to be equal to 11. So I can keep following this rule and I can generate every element of my sequence starting from this initial term A of 0 is equal to 2. So I can represent my sequence here. The first term of the sequence is 2, then 5, then 8, then 11, and then so on. Okay, so we're going to focus on this kind of a representation of a sequence where the one or some or initial terms are given, and then a rule is defined which is going to connect the nth term with some preceding terms. Let's look at another example, and through this example we're going to learn how you can represent a sequence A of n by finding some initial terms and by finding a rule which is going to relate these terms of this sequence. Okay, so for example, we have a sequence which is defined in an explicit way based on the formula that A of n is going to be equal to n factorial, and then this is true for n greater than equal to 0. Okay, so based on this formula of n factorial, I can compute the first term of my sequence A0 in an explicit way is going to be equal to 0 factorial, and 0 factorial is going to be equal to 1. The second term is going to be A of 1. A of 1 is 1 factorial, and 1 factorial is going to be equal to 1. Then my A of 2 term is 2 factorial. 2 factorial is going to be equal to 2. A of 3 is 3 factorial. 3 factorial is going to be equal to 6. Okay, and by following this an explicit formula, I can compute every element of my sequence. Okay, so my A of n sequence which you generate through this explicit formula is going to be 1, 1, 2, 6, and then 24, 120, and so on. Okay, now let's suppose either the sequence is given in the form of this explicit formula or the sequence is given in the form of these terms. Then the question is, can you find another representation of this sequence in the form of some initial terms, as well as finding some rule which connects the element of this sequence? Okay, and then you can apply the definition of n factorial. So from the definition of n factorial, you can say n factorial is basically the product of n and all preceding terms all the way up to 1. Similarly, we can define n minus 1 factorial is the product of n minus 1 times n minus 2 all the way up to 1. And then we can relate these two, 1 and 2. So if you look at this part of your n factorial, which is the product of n minus 1 times n minus 2 all the way up to 1, this is nothing but your n minus 1 factorial. So if you replace this part by n minus 1 factorial, then you can represent your n factorial is nothing but n times n minus 1 factorial. Okay, if you write this n factorial in terms of your nth term and n minus 1 term of the sequence, then you can say my nth term of the sequence A of n is represented by n factorial here. My n minus 1 terms of this sequence are represented by n minus 1 factorial here, and they are connected through this rule that A of n can be written as n times of a n minus 1 for every value of n greater than equal to 1, and I just have to pass this initial condition or the initial term value, and in that case if I choose my A of 0 is equal to 1, that's going to solve my purpose, and I can use this initial condition and I can use this rule to represent the same sequence which I was generating through that explicit formula. So you can start by passing this value. A of 0 is 1. So the sequence which you are generating is 1 is going to be the first element. Then if you pass the value of n equal to 1 here, so you are saying A of 1 is written as 1 times A of 0. A of 0 is 1, so is 1 times 1 is going to be equal to 1. The another element of this sequence is 1. Similarly, you can get A of 2. A of 2 is your 2 times of A of 1, which is equal to 2 times of 1, which is going to be equal to 2. So the next element is 2. And you can keep doing the same thing and you can generate every element of this sequence. Okay, so this is the way if an explicit formula is given to you or if a sequence is given to you, then you can try to find some kind of a initial terms which you need to initialize, which you cannot generate through that rule, and rest of the terms you can generate through this rule. Then you find that rule and you say my sequence is now represented in the form of a initial terms and with the help of this rule. So in this example, the nth term is related with your n minus 1 terms and only one initial terms was given. Let's look at another example where you need to define more initial terms and then you have a relationship between your nth term and some more previous terms. So in this example, let's suppose we have a given sequence A of n, where the terms of the sequence is defined by 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. And can you find some kind of a relationship between those terms and some kind of a rule, some kind of a initial condition which is required to define this sequence? So from here we can start assigning the term of my sequence. I'm saying the a of 0 term is going to be equal to 0, a of 1 term is going to be equal to 1, a of 2 is 1, a of 3 is 2, a of 4 is going to be equal to 3, and so on. So what you can observe from here, that if we just take a of 0 is 0 and a of 1 is equal to 1, then a of 2 you can write as the sum of the a of 0 and a of 1. A of 3 can be written as the sum of a of 2 plus a of 1. A of 4 can be written as the sum of a of 3 and plus a of 2. So you can find a rule here, and you can say if you take the initial terms a of 0 equal to 0, a of 1 is equal to 1, then all other terms you can compute here by following this rule, where the nth term, a of n terms, can be related with the two previous term is the sum of the two previous term, that a of n can be written as a of n minus 1 plus a of n minus 2 for every value of n greater than equal to 2. Okay, and this is the famous Fibonacci sequence which you can obtain by following these rules and by following those initial conditions. So through these two examples, you can notice one thing. If a of n is related with the two previous terms, a of n minus 1 and a of n minus 2, then you require two initial terms to define, such that you can have some initial terms and a rule to generate that possible sequence. In our previous example, we have seen if an is related with an minus 1, so it's related with only one previous term, then we required only one initial condition or one initial terms to generate that particular sequence. Okay, so now you can generalize this concept, and you can say if an is related with k previous term, then you required k initial terms to define, such that through those k initial term as well as by the rule which you have established a relationship between the nth term and k previous term, then these two is going to help you in generating a sequence. So now we are in a position to define our recurrence relation. So a recurrence relation for a sequence a of n is an equation that expresses the a of n term in term of one or more previous terms of the sequence. Okay, and namely a of n is related with a0, a1, a2 all the way up to the an minus 1 terms, where and n naught is a non-negative integer. So once we have a recurrence relation which relate the a of n terms with all one or more previous terms, we can say a sequence which you generate a of n is called the solution of recurrence relation if its terms satisfy that recurrence relation. Okay, and another important thing about the recurrence relation is that the recurrence relation is useful for recursively defining a sequence, and we have seen these two examples that how you use recursively the recurrence relation to define the element of a sequence. When it comes to solving a recurrence relation, that means we are trying to find a formula for the nth term of a sequence a of n generated by this recurrence relation, and that's the meaning of solving a recurrence relation. And such formula for a of n term is called the closed formula to generate that sequence or to solve that recurrence relation. In this lecture, we're going to study various methods to solve a recurrence relation. So our first method is based on an iterative technique, which comes in a class of iterative method. And first kind of the iterative method is when you work upward Okay, and you do the forward substitution with that. So this method is you are working upward and doing the forward substitution. Let's suppose you are trying to solve this example where the initial condition or the initial term a of 1 is defined as 2, and then you have a rule that you're connecting the nth term with n minus 1 terms by this formula that a of n is going to be equal to a of n minus 1 plus of 3, where this relation is holds for every value of n greater than equal to 2. Okay, so we have seen this example that through this initial terms and through this recurrence relation, you can generate a sequence where the first term of the sequence is 2, and then you're going to have a 5, then 8, then 11, and so on. Okay, now the question is, can you find some kind of an explicit formula to define this nth term of that sequence? That means, can you find the solution of this recurrence relation, or can you find the closed formula to generate that sequence or to solve that recurrence relation? Okay, so in the technique of working upward and doing the forward substitution, what you do, you start from your second term a of 2. So because you are working upward, so after a1 you're going to generate a2, and a2 is going to be equal to a1 plus 3 based on this recurrence relation, and a1 plus 3 is 2 plus 3, and 2 plus 3 you can represent as 2 plus 1 times of 3. Okay, similarly a3 can be written as a2 plus 3 by following the recurrence relation. a2 is already 2 plus 3, so you're going to replace it here, and plus 3 is going to remain as it is, which you can rewrite as nothing but 2 plus 3 plus 3, and 2 plus 3 plus 3 can be represented as 2 plus 2 times of 3. Okay, next you generate the term a of 4. a of 4 is going to be equal to a of 3 plus 3 by using this recurrence relation, which you can write as nothing but 2 plus 3 plus 3 and plus of 3, because this part comes from your a of 3 term, and which you can write as 2 plus 3 plus 3 plus 3, so which you can write as 2 plus 3 times of 3. If you keep following this, then you can say the nth term of this sequence a of n can be generated by a of n minus 1 plus of 3, and a of n minus 1 plus of 3 can be written as 2 plus 3 plus 3 plus 3 all the way up to 3, and those are n minus 2 3's here. This is basically equal to your a of n minus 1 term, and then you are adding a plus 3 here because of this plus 3. Then if you just add everything together, so you're saying 2 is going to remain as it is, and you have n minus 2 3 here, and you have 1 3 here, so in total you have a n minus 1 times of 3. Okay, so based on this rule of working upward, so you're starting working upward, you're starting from a1, then you generate a2, a3, a4, and doing this forward substitution, you are able to generate a formula for your nth term of this sequence, and a of n from here can be written as 2 plus 3 times of n minus 1, and if you simplify, you will have the formula for your nth term as 3 times of n minus 1. Okay, so this is your closed formula, which is the solution of your recurrence relation. Okay, so this is your first method when we move forward and we do this substitution. This is your working upward and doing the forward substitution method, and this way you are able to generate some closed formula for your nth term of that sequence, which is going to solve your recurrence relation. Our second method is based on the approach of working downward and doing this backward substitution. So in this approach, we start from the nth term of this sequence a of n, and a of n from this rule can be written as a of n minus 1 plus of 3. While we know that a of n minus 1 can also be represented by this rule that a of n minus 1 can be written as a of n minus 2 plus of 3, and if we replace a of n minus 1 by this term from here, it can be written of a of n minus 2 plus of 3, and plus of 3 is going to remain same here. So everything you can write here as a of n minus 2 plus 2 times of 3. Okay. Similarly, you can represent your a of n minus 2 term as nothing but a of n minus 3 plus 3. The plus 3 is going to remain same. This 3 is going to remain same. This you can write as a of n minus 2 plus 3 times of 3. If you keep on following the same thing, the same pattern by moving downward, you can represent this is going to be equal to a of n is going to be equal to a of 2 plus n minus 2 times of 3. Okay, and once you replace a of 2 by a of 1 plus 3 and n minus 2 times 3 going to remain same, you can simplify and you can represent your a of n is nothing but a1 plus n minus 1 times of 3. Okay, now remember you have initial condition or initial terms which is given here, that a of 1 is going to be equal to 2, and then you put this value in your above equation. Then if you replace a1 by 2, a of n can be written as 2 plus 3 times of n minus 1, which is equal to 3 of n minus 1. So the closed formula which you obtain from this method is the same which you obtained from the previous method, and you are saying is a closed formula because this is going to be the solution of your recurrence relation. Now this trick of solving the recurrence relation work for certain examples where we can move upward and we can do this forward substitution, or we can move or downward, or we can do this backward substitution, but it's not going to work for every example. And then the natural question is, given an arbitrarily recurrence relation, is there a systematical way or a mechanical way to obtain the closed form solution of the recurrence relation? And the answer of this problem is not for any arbitrarily recurrence relation, but there exists a subclass of the recurrence relation for which we can have a systematic way to solve them. Okay, and that's going to be focus of this lecture now. So in this lecture we're going to focus on a linear recurrence relation with constant coefficient, which can be defined with the help of this recurrence relation, which have the following form, where a of n can be written as c1 times of a n minus 1 plus c2 times of n minus 2, and all the way up to ck times of a n minus k plus your f of n term, where each ci's, they are the constant, and c of k is not going to be equal to 0 here. Okay, so then based on this f of n function, if f of n is going to be equal to 0, then it is called as a linear homogeneous recurrence relation with constant coefficient. Okay, since each term is linear here, that's the reason you are saying is a linear. Since this function f of n is 0 here, you are saying is a homogeneous, and the recurrence relation because there's a relationship between the nth term and some previous terms up to n minus k, and this is a recurrence relation with a constant coefficient because the coefficient c of i's, they are the constant here. Okay, so the name of this kind of a relation is a linear homogeneous recurrence relation with constant coefficients. Okay, in the another case where your f of n is not equal to 0, when this term, you can have an example of a constant term, a function of n square and so on, 2 to the power n. So in that case, this becomes a linear non-homogeneous recurrence relation with constant coefficients. Okay, also when a of n term is related with your a of n minus k terms, when your c of k is not going to be equal to 0, then you will say the k is basically the degree of this recurrence relation. Let's look at some example here. So in our first example, when a of n is written as a of n minus 1 plus 2 times of a of n minus 5, then the f of n term here is 0. Okay, so this is a case of, and every terms here is a linear term, and they have a constant coefficient, so the coefficient is 1 here. So this is an example of a linear homogeneous recurrence relation with constant coefficient. Since a of n is connected with a of n minus 5, so the degree of this recurrence relation is 5. In your second example, when you write a of n equal to 2 times of a n minus 2 plus 5, now you have a non-homogeneous terms here, f of n equal to 5. Okay, since f of n equal to 5 here, but still you have a case of a linear recurrence relation with a constant coefficient. So this is an example of a linear non-homogeneous recurrence relation with a constant coefficient, and the degree of this recurrence relation is 2. Similarly, you can have a third example when a of n is going to be equal to a of n minus 1 plus of n. Then in this case, your f of n is going to be equal to n, which is not equal to 0. So you have a case of a linear non-homogeneous recurrence relation with constant coefficients, and since a of n is connected with a of n minus 1, so the degree of this recurrence relation is 1. Now you take the fourth example when a of n is written as the product of a of n minus 1 times a of n minus 2, and then we say is not going to be a linear recurrence relation, is going to be a non-linear recurrence relation. Okay, so the degree here could be 2 because a of n is related with your a of n minus 2. Similarly, at the next example where a of n is related with n times of a of n minus 1 plus a of n minus 2. So you will see here the coefficient of a of n minus 1 is n, which is not a constant. So this is not the problem with a constant coefficient recurrence relation. This is the problem with non-constant coefficient, and the degree of this recurrence relation is 2. So in this lecture, we are only going to focus on those linear homogeneous and linear non-homogeneous recurrence relation with constant coefficient. So first we are going to focus on the problem of how to solve a linear homogeneous recurrence relation with constant coefficient, and one of the tools which you are going to use in solving those recurrence relation is based on your characteristic equations. And characteristic equation you can obtain by assuming that, let's suppose a of n is equal to r of n, where r is not equal to 0 and is a constant, is a solution of the homogeneous linear recurrence relation of degree k with constant coefficient, which is given here with this expression, where a of n can be written as c1 times of a n minus 1 plus c2 times of a n minus 2 all the way up to ck times of a n minus k. Okay. Since you are assuming that a of n is equal to r of n is the solution of this linear homogeneous recurrence relation with a constant coefficient, that means is going to satisfy this linear recurrence relation. So you start by putting a of n is equal to r of n. Then by following the same rule, a of n minus 1 becomes r to the power n minus 1. A of n minus 2 will become r to the power n minus 2, and a of n minus k will become r to the power n minus k. Then you replace each ai's terms in this linear recurrence relation by this r to the power kth term. So a of n can be replaced by r of n, a of n minus 1 can be replaced by r to the power n minus 1, a of n minus 2 can be replaced by r to the power n minus 2, and similarly a of n minus k can be replaced by r to the power n minus k. So this homogeneous linear recurrence relation will transform in the form of this equation in terms of r, and then you divide everything by r to the power n minus k. Since you have assumed that r is not going to be equal to 0, you can divide both sides by this factor of r to the power n minus k, and then if you divide r to the power n by r to the power n minus k, that will be equal to your r of k. So when you divide this term by r to the power n minus k, then you will get r to the power k. So this side will be your r to the power k, and similarly you can divide r of n to the power n minus 1 divided by r to the power n minus k. That will be equal to your r of k minus 1. Okay, and you keep doing the same thing. You will see that once you divide this equation by r to the power n minus k term, then this equation will change to this form. Okay, and if you take this right hand side to the left side, then you can say this equation is nothing but r to the power k minus c1 r to the power k minus 1 minus c2 r to the power k minus 2 all the way up to minus c of k equal to 0. So such equation has a special name and is called the characteristic equation, and the roots of this characteristic equation they call the characteristic roots. Okay, so we're going to use this characteristic equation and these characteristic roots when we write the solution of a linear homogeneous recurrence relation with constant coefficient. Let's look at one example and see how you find the characteristic equation and its roots for the following recurrence relation, where my recurrence relation A of is given as A of n is equal to A of n minus 1 plus 2 times of A n minus 2 is a recurrence relation which is linear, which is homogeneous, and is going to be with constant coefficient, and the degree of this recurrence relation is 2 because A of n term is connected with A of n minus 2 term. Okay, now to get the characteristic equation, we start by assuming that A of n is equal to r to the power n is the solution of this recurrence relation. Then A of n minus 1 becomes r to the power n minus 1, A of n minus 2 becomes r to the power n minus 2, and then you put that value in your recurrence relation. So the recurrence relation will convert into the following form, is going to be equal to r to the power n equal to r to the power n minus 1 plus 2 times of r to the power n minus 2. And since r is not equal to 0, you can divide the whole expression by this term r of n r to the power n minus 2, and this equation can be transformed to the equation like r square is going to be equal to r plus 2. When you take the right side r plus 2 to the left side, then this equation becomes r square minus of r minus of 2 equal to 0, and which is nothing but your characteristic equation with respect to this recurrence relation. If you simplify this, you can write is nothing but a factor of r minus 2 plus r plus 1 equal to 0, and that means the roots of this characteristic equation is 2 and minus 1, and 2 and minus 1 becomes the characteristics roots of this. Okay, so that's the way you build the characteristic equation for any given recurrence relation, and once you simplify that characteristic equation, you can find those factors, those becomes your characteristic roots. So the one thing you will notice when you find the roots of the characteristic equation, sometimes they can be distinct and sometimes they are not distinct. Like for the example here, they are distinct because 2 is not going to be equal to minus 1, but you can see some example when you will have the same characteristic roots, or some of the characteristic roots are equal, some are unequal. So in case of your characteristic equation of degree 2, you can only have these two possibility, either the roots are going to be equal or the roots is not going to be equal. So if they are not equal, we'll say is a distinct. If they are equal, we'll say they are the equal cases. Okay, but if you have a characteristic equation of degree 3, 4 and more than that, then you can have a mixed cases, like so we'll say the case will be distinct when all the roots are different. Otherwise, we will say the case is not distinct if some of the roots are equal, some of the roots are not equal. Okay, so the distinct word we are going to use only for the cases when we have the characteristic roots, which all of them they are different. So the first theorem and first result which we are going to use to write the solution of your linear homogeneous recurrence relation of degree k, which is written here, when the characteristic roots of this linear recurrence relation they are distinct. So if is a linear recurrence relation of degree k, so your characteristic equation will be a polynomial in term of r of degree k. So the first case it may happen that all of the roots of the characteristic equations they are distinct. So we will have the k distinct roots, and those roots, let's suppose those are your r1, r2, r3 all the way up to r of k. And if they are different or if they are distinct, then the closed form solution for your expression a of n can be given as alpha 1 times of r1 to the power n plus alpha 2 times of r to the power n, and all the way up to alpha k times of r to the power rk to the power n. Okay, so these constant alpha 1, alpha 2 and all the way up to alpha k, they can be uniquely determined based on the k initial condition which your recurrence relation of degree k should have to form a sequence. Let's look at one example how to find a closed form solution of a recurrence relation which is given by two initial terms or initial condition as a of 0 is equal to 2 and a of 1 is equal to 7, and all other terms of this sequence can be generated through this relation where a of n is related with a of n minus 1 plus 2 times of a of n minus 2. And from this recurrence relation we can say is a linear homogeneous recurrence relation with constant coefficient and two initial conditions are given here. So the first step is we're going to build the characteristic equation, and we have seen this example before. The characteristic equation of this relation is r square minus of r minus of 2 is going to be equal to 0. The roots of the characteristic equation are 2 and minus 1, and both the roots are distinct, they are not equal. And then we can apply our theorem. Then based on our theorem, the closed form solution a of n can be written as alpha 1 times of r1 to the power n plus alpha 2 times of r2 to the power n. Okay. Now r1 and r2 are the roots of my characteristic polynomial, so they are 2 and minus 1. So I can write my closed form solution is nothing but alpha 1 times of 2 to the power n plus alpha 2 times of minus 1 to the power n, where alpha 1 and alpha 2 are two constant which I can uniquely determine based on my initial condition, and my initial condition in this case is given as a of 0 is 2 and a of 1 is going to be equal to 7. So once I have an expression for a of n in terms of my characteristic roots which is given by this equation 1, I can put n is equal to 0 in this equation. Then this side becomes a of 0 and this side becomes alpha 1 times of 2 to the power 0 plus alpha 2 times of minus 1 to the power 0. Since a of 0 is 2, so this side becomes 2 and that side will becomes alpha 1 plus alpha of 2. So this is my second equation. Similarly, I can use the another initial condition with respect to n is equal to 1, and then my closed form of the solution a of n with the value of a1 is equal to 7, it gives me that a of 1 is going to be equal to alpha 1 times of 2 to the power 1 plus alpha 2 times of minus 1 to the power 1, which is going to be equal to a1 is 7, so this side is going to be 7, and once you simplify it, this is going to be 2 of alpha 1 minus of alpha 2. So this is going to be my third equation. Now I have two equations, equation 2 and equation 3. And I have two unknowns alpha 1 and alpha 2, and to compute those two unknown alpha 1 and alpha 2 I'm going to use this second and third equation. So I have my second equation here, 2 is going to be equal to alpha 1 plus alpha 2 and 7 is going to be equal to my 2 of alpha 1 minus of alpha 2, and if I add both the equation together, so this is your alpha 2 minus of alpha 2, this side will cancel your alpha 2 contribution, so you will have alpha 1 plus 2 of alpha 1 is 3 alpha 1 this side, and 2 plus 7 9 is going to be this side. Once you simplify, then your value of alpha 1 is going to be equal to 3, and once alpha 1 is going to be equal to 3, you can put the value of alpha 1 in your second equation. Okay, and from there you can obtain the value of alpha 2, and alpha 2 comes out to be minus of 1. Once you know the value of your constant alpha 1 and alpha 2, you can put them into the closed form of your solution of your recurrence relation, and then the solution of your recurrence relation, which is the unique solution now, is going to be 3 times 2 to the power n minus 1 to the power n. Okay, so this way we use the concept of characteristic equation, characteristic roots, and the theorem which we saw in solving the recurrence relation. So far we have seen an example and the result of our theorem which is going to apply if our characteristic roots are distinct, and how to solve the recurrence relation with respect to that case. So the natural question is, what will happen if those characteristic roots are not distinct? Okay, so if they are not distinct, they could be equal, or they could be some are equal and some are not equal, but they don't belong to the category of distinct roots. So in that case we have this generalized theorem, and we are not writing the proof of these theorems because they required a knowledge of linear algebra which you don't have right now. This is the course maybe you're willing to take in future. So the result of this theorem says that let a of n is equal to c1 times a of n minus 1 plus c2 times of a n minus 2 and all the way up to ck times of a n minus k be a recurrence relation. Is going to be a recurrence relation of degree k, and it have t distinct characteristic roots r1, r2 and rt. Okay, remember this is a recurrence relation of degree k. The characteristic equation should be a polynomial in term of r of degree k, but here we are assuming that the case when the characteristic roots are not distinct, but some of the roots are going to be equal and some of the roots are not going to be equal. So let's suppose it will have t number of distinct roots. Okay, and out of these t distinct characteristic roots, some of them they are repeating. So we are assuming those t distinct characteristic roots r1, r2 all the way up to r of t with certain multiplicity. And let's suppose the multiplicity of r1 is m1, multiplicity of r2 is m2, and all the way the multiplicity of r of t is m of t. In such a way that if we add all those multiplicity together, that's going to be equal to k, and that's the degree of my recurrence relation. Then the closed form solution of my recurrence relation can be given by this expression, where a of n is written as summation. I is going to apply from 1 to t, since we are assuming we have t distinct characteristic roots, and they're going to repeat with a multiplicity of m of t. So we're going to write this summation going to hold with the repeated roots. So it's going to be alpha i0 plus alpha i1 times of n plus all the way up to alpha I times m minus 1 multiplied by n to the power m of I minus 1 and multiplying everything by r of I to the power n, which if you expand then can be written as for I equal to 1 is going to be alpha 10 plus alpha 11 times of n plus all the way up to alpha 1 m1 minus 1 times of n to the power m1 minus 1 and multiplying with r1 to the power n, and then you keep writing for every value of I is 2, 3, 4, and the last value for t is going to be alpha t0 plus alpha t1 times of n plus all the way up to alpha t mt minus 1 times n to the power mt minus 1 and multiplying by rt to the power n, where the distinct behavior of the roots is recording with this factor of r1 to the power n and then all the way up to rt to the power n, since we have t distinct roots and all the roots are repeating with certain multiplicity. So for example r1 roots is repeating with a multiplicity of m1, so this expression is because they are having a multiplicity of m1, and similarly rt roots are having a multiplicity of m2 mt, so this expression is with respect to that multiplicity of m of t. Okay, so once we have this theorem which can be applicable for the case of solving a recurrence relation when the characteristic roots are not distinct, so we can see some example and how to apply it. So our first example is try to find the closed form solution of the following recurrence relation, where they have two initial conditions and the recurrence relation will be of degree 2, which is a linear homogeneous recurrence relation with constant coefficient. So in that case we can check and find our characteristic equation. So if you put a of n is equal to r to the power n, a of n minus 1 is equal to r to the power n minus 1, a of n minus 2 is equal to r to the power n minus 2, where r is not going to be equal to 0, is going to be a constant number. Okay, then if you put that in your recurrence relation, then a of n equal to 6 a of n minus 1 and minus of 9 a of n minus 2, it will convert to r to the power n, and 6 of r to the power n minus 1 minus 9 of r to the power n minus 2. And if you divide everything by r to the power n minus 2 both sides, so this side will be equal to your r square, this side will be your 6 of r minus of 9. okay, which if you rewrite then can write as r square minus 6 of r plus of 9 equal to 0. So that is the characteristic equation which we have it here, which can be written as the product of r minus 3 times r minus 3, and if you put that equal to 0, so the root of this characteristic equation, they both are 3, so they are not distinct and they are repeating and they are same. So now from our previous theorem we can write the closed form solution of this homogeneous linear recurrence relation of degree 2, which have two characteristic roots and they are not distinct, they are same. So my a of n can be written as alpha 0 plus alpha 1 times of n, and multiplying by this 3 to the power n terms, because my r terms here is going to be equal to r1 equal to r2, they both are 3. Okay, where alpha 0 and alpha 1 are the constant which I can determine based on my initial condition, and I have two initial condition here. a0 is going to be equal to 1 and a1 is going to be equal to 6. So for n is equal to 0, if you put in your closed form of the solution, this side will be your a of 0, and then this side will be your alpha 0 plus alpha 1 times of 0 times 3 to the power 0, which if you simplify, then the value of the constant alpha 0, which will be equal to 1. While for the case of n equal to 1, if you put in your closed form solution, this side will be your a of 1, this side will be your alpha 0 plus alpha 1 times of 1 times of 3 to the power 1, and if you simplify, this is going to be equal to 6 is going to be equal to alpha 0 plus alpha 1 times of 3, and on simplification you will get equation that alpha 0 plus alpha of 1 is going to be equal to 2. Since alpha 0 is already 1, alpha 1 from this equation comes out to be equal to 1. And by placing the value of alpha 0 and alpha 1 in your closed form of the solution, you have the final form of your solution a of n is 1 plus n times 3 to the power n. So that is the solution of your problem in the case when the root are not distinct in example of a second degree recurrence relation. Let's look at another example, and this time we have a recurrence relation of degree 3 where my term a of n is related with a of n minus 3, and I have an example of a linear homogeneous recurrence relation with constant coefficient. I have three initial conditions a0, a1 and a2. Now to solve this problem we follow the same approach. We assume that a of n equal to r to the power n, where r is not equal to 0, is a constant, is going to be the solution of this recurrence relation. And similarly you can write your a of n minus term, n minus 1 is going to be equal to r to the power n minus 1, a of n minus 2 is going to be equal to your r to the power n minus 2, and a of n minus 3 is going to be equal to r to the power n minus 3. And when you substitute the value of an minus 1, an minus 2, an minus 3 into your given recurrence relation, then you say this side can be written as r to the power n, this side will be your minus 3 r to the power n minus 1, minus 3 r to the power n minus 2, and minus r to the power n minus 3. And then you divide the both side by this factor of r to the power n minus 3, and you take the right side to the left side, you will have this characteristic equation. Since this is a linear recurrence relation of degree 3, you will have a characteristic equation in terms of the variable r of degree 3. And this characteristic equation you can simply represent with the term of r plus 1 to whole cube. And this gives you the characteristic roots, and the roots are not distinct here. All three roots are equal. So they are equal to minus 1, minus 1 and minus 1. So in another way you can say the root r equal to minus 1 is going to have a multiplicity equal to 3. Okay, now we can apply our generalized theorem in case when you have a characteristic roots which are not distinct. So my closed form of the solution a of n can be written as alpha 0 plus alpha 1 times of n plus alpha 2 times of n square, and multiplying with r to the power n, and r in this case is going to be equal to minus 1, so minus 1 to the power n, where alpha 0, alpha 1 and alpha 2 are three constants here which we can determine based on our three initial condition. And our initial condition in this case is a0 is going to be equal to 1, a1 is going to be equal to -2, and a2 is going to be equal to -1. So for n is equal to 0, if we put n equal to 0 in our closed form of the solution, so this side will be your a0 and the right hand side will be your alpha 0 plus alpha 1 times of 0 plus alpha 2 times of 0 square times -1 to the power 0, which if you simplify is going to give you the solution as alpha 0 is going to be equal to 1. Now for n is equal to 1, you can have this side is going to be your a1, this side will be your alpha 0 plus alpha 1 times of 1 plus alpha 2 times of 1 square, and multiplying with -1 to the power 1, which if you simplify you will get 2 is going to be equal to alpha 0 plus alpha 1 plus alpha of 2. Similarly, by using the third initial condition for n is equal to 2, you will have this side from your closed form solution equal to a of 2, and just by putting n is equal to 2 in your closed form solution, this side will be your alpha 0 plus alpha 1 times of 2 plus alpha 2 times of 2 square, and multiplying by -1 to the power 2, which will be equal to -1 is going to be equal to alpha 0 plus 2 of alpha 1 plus 4 of alpha 2. So we will have second, third and 4. We have three equations and we have three unknowns to determine, and one of the unknown is already obtained from your equation 2, so my value of alpha 0 is going to be equal to 1. So you can use that value of alpha 0 in your third and fourth equation, and once you put alpha 0 equal to 1 in your third equation, your equation will change to 1 is going to be equal to alpha 1 plus alpha 2. Once you put alpha 0 equal to 1 in your fourth equation, that equation will convert to -2 is going to be equal to 2 times of alpha 1 plus 4 of alpha 2. Okay, so then you can multiply by 2 to this equation. Okay, so if you multiply by 2, this equation becomes, this side will be 2, this side will be 2 of alpha 1 plus 2 of alpha 2, and you keep this equation, second equation, as it is. So this side will be your -2, then plus of -2 is going to be equal to 2 of alpha 1 plus 4 of alpha 2. Now if you subtract your below equation from the above equation, then this side will be 2 minus of 2 is going to be equal to 4. This side will be the 2 of alpha 1 minus of 2 of alpha 1, this will cancel out, and 2 of alpha 2 minus 4 of alpha 2 will be your -2 of alpha 2. So from there you can get the value of alpha 2 equal to -2, and once alpha 2 is equal to -2, you can use this equation that alpha 1 plus alpha 2 was equal to 1, so we can get the value of alpha 1, which is going to be equal to 3. Once you have the value of alpha 1, alpha 2 and alpha 0, you can put those values into your closed form of the solution, and then you will have a unique solution, and your final form of the closed form solution will be 1 plus 3 of n minus 2 of n square and times of -1 to the power n. Okay, so this is the solution of your homogeneous linear recurrence relation of degree 3 for this example. Okay, so in this class we learned the concept of recurrence relation. We learned how to represent the sequences in terms of the recurrence relation. We learned how to solve some recurrence relation by using your forward and backward substitution method. We learned a systematic way based on your characteristic equations and characteristic roots how to solve your homogeneous linear recurrence relation of degree k, and in the case when the roots are distinct and when the roots are not distinct. And in our next lecture we're going to learn how to extend this idea for the case of solving a non-homogeneous linear recurrence relation with constant coefficient, and then we're going to learn about divide and conquer technique as well as the master theorem, how to apply the master theorem in solving those kind of problems.